Hello students. In today's deliberation, we will talk on the topic Early Earth. The main objectives of present deliberation will be to know about Earth. Secondly, we will get idea of early Earth. We will also focus on theories about origin of universe, and we will have a deliberation on how atmosphere originated, and we will also discuss the importance of photosynthesis for the atmosphere. Let me first begin with the introduction of our Earth. Of all the planets of the solar system, our Earth is unique. It is the only planet known to harbor life of wide variety, from the simplest one-celled organisms to the most complex ones like human beings. The origin of Earth has always been a mystery for humans. After formation some 4,500 million years ago, the Earth has undergone several upheavals in its structure to come to the present shape. The continents that we see today were not there always. They have been in constant motion for hundreds of millions of years. The violent activities inside Earth also gave rise to most valuable resources like coal, oil, and natural gas. The first life forms, bacteria-like organisms, appeared on Earth some 3,500 million years ago. All the planets of the solar system have now been explored by spacecrafts, and we know that water, which is essential for life, exists only in this planet. Nowhere else can one enjoy the scenic beauty that we see on this planet. There are mountains and volcanoes on other planets, but they do not evoke the joy and wonder as they do on Earth. Now the question is, what makes our planet so different from others? Our Earth happens to be at just the right distance from the Sun. It's neither too close nor too far. Had it been a little closer to the Sun, it would have been too hot for the life. On the other hand, if it were a little farther away, it would have been too cold. Distance from the Sun is also the key factor that makes Earth the only planet with liquid water on the surface. So, it is firstly distance what makes Earth unique one. Water is vital not only for biosphere, the part of Earth where life exists, but also for geological processes of erosion, transport, and deposition that shapes the Earth's surface. Yet, if the Earth were closer to Sun, the water would have vaporized. If it were farther, water would have turned to ice. Earth is the only planet that has liquid water. Believe it or not, all naturally occurring elements, which are building blocks for all forms of matter, both the living and non-living, originated in the cores of stars. The study of the origin and build-up of these elements in these stars is called a nucleosynthesis. Now, let's move to the second part of our topic, that is origin of universe. There are two theories pertaining to the origin of universe: static theory and the evolutionary or Big Bang theory. Static theory propounds that the universe did not have a beginning time and the matter is being created on continuous basis. This is what static theory says. On the other hand, Big Bang theory supports the idea that the universe had a beginning time. It advocates that the universe was created at time t0 about 10 billion years ago, when a hyperdense sphere of matter packed into volume roughly that of a solar system with extremely high density and temperature exploded in a Big Bang at or near the velocity of light. What is relevant about the Big Bang is astronomical evidences are in the favor of Big Bang theory. Hence, it is the most accepted theory for the origin of universe. Big Bang was not limited to explosion, but it has eras associated with it. Let us discuss them now. The Big Bang divides the history of universe into three eras: radiation era, matter era, and the life era. Each era is subdivided into a number of epochs, and each epoch corresponds to a specific period in the build-up of the universe. Let's now first the radiation era. The hyperdense pair of matter which caused the Big Bang was giant neutron ball consisting of 10 to the raised power 78 to 10 to the raised power 79 neutrons. This ball is often referred to as primordial matter or yelm. The temperature of this yelm was 10 to the raised power 30 Kelvin. There were three epochs of this era: chaos epoch, Hadron epoch, and the lepton epoch. During the first three epochs, the radiation density exceeded the matter density by large amount of photons of radiation, outnumbered particles of the matter. As soon as the elementary particles of matter had begun to coagulate, radiation destroyed them. Second is the matter era. The matter era consists of three more epochs: atom epoch, galaxy epoch, and the stellar epoch. In the matter epoch, matter dominated the radiations as the principal constituents of the universe. Galaxy epoch resulted in decrease of the temperature of the universe, and universe became thinner, colder, and darker. Stellar epoch was a period when formation of stars took place. During the matter era, matter prevailed while radiation subsided. Last is the life era. The atoms formed in the universe combined to give molecules. Since these molecules were formed in the space, they were called as interstellar molecules. Initially, these molecules were simple in composition, but gradually more complex molecules were formed. This decrease in complexity of molecules with the passage of time is called as chemical evolution. Hence, life era was associated with emergence of life. So students, after knowing about the Big Bang and the Earth, let's shift our focus to know more about early Earth. The early Earth was very different from the world we know today. There were no oceans, no oxygen in the atmosphere, and no living beings. Rocks and other materials left over from the formation of solar system were constantly raining down from sky. As a result of this bombardment and the heat generated from the radioactive decay within the Earth and from the pressure of contraction, Earth at this stage was extremely hot and fully molten. Heavier elements sank to the center while lighter ones rose to the surface, producing Earth's various layers. Earth's early atmosphere was mostly probably made of gases from the solar nebula, especially light gases such as hydrogen and helium. But the solar winds and the Earth's own heat would have driven off this atmosphere. As the Earth cooled and shrunk, gravitational attraction became strong enough to retain an atmosphere which included water vapor. The surface cooled quickly, forming the solid crust within a span of some 100 million years. Between 4,000 and 3,800 million years ago, as the Earth underwent a period of heavy bombardment by asteroids, steam escaped from the crust while more gases were released by volcanoes, making up an atmosphere made mostly of nitrogen, carbon dioxide, carbon monoxide, and water vapor, possibly with small amounts of methane and ammonia. Any free oxygen in the atmosphere at this stage would have been bound by hydrogen or minerals on the surface. As the temperature dropped further, clouds formed and condensed and fell as rain. As time passed, rocks on the surface absorbed most of the first rains. As torrential rains continued, water collected in vast basins and became the first seas. Now, let's talk about Earth as dynamic planet. After its birth, some 4,500 million years ago, the Earth had not remained the same. The continents that we see today were not there always. They have been in constant motion for hundreds of millions of years. The world's tallest mountain range, the Himalayas, rose from under the sea some 50 million years ago. Volcanic activity, earthquakes, winds, and tidal waves have been constantly acting, shaping, and reshaping Earth's surface. Rocks formed by geological processes form a key ingredient of our economy. They provide mineral resources, building materials, and raw materials for industrial processes. The surface of Earth was harsh at the time of its birth, about 4.5 billion years ago. Red-hot oceans of magma, massive meteorite strikes, and a dense atmosphere elicit the name Hadean for the earliest time period. The atmosphere of our planet did not originally contain all the free breathable oxygen it does now. The first permanent atmosphere arose when the gases that has been dissolved in the molten planet during its assembly from smaller bodies called planetesimals were released to the surface by volcanism. The first primitive atmosphere was probably several times denser than what we have now, and was dominated not by oxygen but by carbon dioxide, a major greenhouse gas. Astrophysical computer models, based on the study of young stars and of star-forming regions in the galaxy, strongly suggest that the Sun was much dimmer when the first life emerged on Earth over 4.5 billion years ago. A dimmer Sun would have supplied less solar radiations to warm the early Earth. To keep the Earth from starting out as a frozen wasteland with no hope for beginning life to take hold, an atmospheric greenhouse must have kept the surface zone warm enough to maintain water in liquid form. Greenhouse gases, mainly water vapor, carbon dioxide and methane, which were in much higher abundance than today, would have formed a thermal blanket over the surface of the early Earth that strongly absorbed outgoing thermal radiation. This leads to a significantly enhanced warming greenhouse effect. As Earth's biosphere and atmosphere co-evolved over billions of years, the product of photosynthesis, mainly free oxygen, has come to dominate the chemistry of the atmosphere. Without the byproducts of crucial biological processes such as photosynthesis, there would be little or no free oxygen for animals to breathe, nor enough to form protective ozone layer in the upper atmosphere. Ozone is formed by the recombination of oxygen by solar radiation in the upper atmosphere into the new molecules with 3 oxygen atoms. This molecule screens harmful ultraviolet sunlight and prevents most of it from reaching the surface. Since little evidence from the Earth's formational time has survived for scientists to study, it's possible to only make a few basic conclusions about the nature of the first atmosphere and the conditions in which life originated. Most of what is known about early planetary history comes from 3 sources: the spare geological record remaining from more than 3.5 billion years ago, computer models of atmospheric changing with time, and comparing Earth to its planetary neighbors, Mars and Venus, which evolved along very different paths. Scientists have also recently started to study the sophisticated biochemical machinery of primitive photosynthetic bacteria to learn more about their early evolution. Friends, let's discuss the major incident of Earth, that is, how Earth's atmosphere originated. The elements and compounds that make up the atmosphere and oceans evaporate readily under normal surface conditions. That is the definition of volatile. Elsewhere in the universe, these volatiles would assume very different physical states. In the space between planets and stars, where it's very cold, they would be present mostly as solid ice. However, near stars or in regions where new stars are being formed, where it's hot, they would be present as plasma. Plasma is in fact the most common state of matter in the universe. Yet, this state is useless for life. Only solid bodies like planets can support matter in the usable, solid, liquid and gaseous state. So friends, the Earth could have started with an atmosphere extremely enriched in carbon dioxide. The rise in land plants after 500 million years ago defines a minimum limit for carbon dioxide in the air after that time. On Earth, volatiles that constitute the atmosphere are principally represented by the gases: nitrogen, which makes up 78%, oxygen 20%, water vapor and argon about 1%, and carbon dioxide 0.03%, and trace amount of other gases. This mixture is very much different from the lifeless atmospheres of nearby Venus and Mars, both of which have no free oxygen and are completely dominated by carbon dioxide. This comparison of atmospheres of our planetary neighborhood illustrates the role of life in maintaining surface conditions open for habitation. The air and the oceans probably represent most of the surface reservoirs of the volatile compounds, nitrogen and water on Earth. Oxygen is dominantly locked in minerals in the Earth's crust and the Earth's interior, and would remain so entirely if not used for the action of photosynthesizers. As for carbon, the amount that is present as carbon dioxide in the atmosphere is small compared to the majority of the Earth's carbon, which is sequestrated in the carbonate rocks such as limestone and marble, organic matter in sediments, fossil fuels and biomass on or near the surface. If all of this carbon were oxidized into carbon dioxide and put into the atmosphere, it would overwhelm all other gaseous components. The amount of carbon dioxide released in such a case would give our planet a surface pressure of about 60 bars and result in an atmospheric composition very similar to that of Venus. There would also be a massive greenhouse effect like the one that keeps the surface of Venus so hot, greater than 460 degrees Celsius. The massive greenhouse effect would result in temperature increase that were more than enough to vaporize the oceans. If the enormous volume of water in the oceans were vaporized, a heavy 250 bar pressure and a deadly greenhouse blanket would push temperatures up beyond even the melting point of rocks. Therefore, it is easy to understand how a delicate balance is necessary among the biosphere, atmosphere, crust and the oceans to keep Earth habitable over long time scales. Over the past few hundred million years, the amount of carbon dioxide in the atmosphere has decreased from high level to stabilize near its present relatively low level. This appears to be a response of the environment to the steady increase in solar luminosity, which has kept the surface within an equitable temperature range for life to flourish over time. Dear students, that's all about today's program. Hope you have understood and enjoyed well. Thank you and goodbye.